Welcome back. So I have a beam here. It has two sections, the horizontal section and the diagonal section. They are both subject to distributed loads as shown in the image. And so your task now is to replace all this distributed loading by an equivalent resultant force that acts at point B, so right here, and the necessary resultant moment that you need in order to make this system equivalent. So good luck, try it out by yourself first, and then see the solutions in the next video. Thank you. Welcome back. Let's now solve this problem and replace all this loading by one resultant force that acts at point B and the necessary resultant moment in order to make it equivalent to this distributed force system here. What I will do first, I will treat the horizontal section and the section at an angle of 60 degrees separately. So I have these two cases here. This one, it's the diagonal section. It's 1.8 meters long. And this one here, it's the horizontal section. It's 1.2 meters long. And of course, the distributed force here is 1 kilonewton over meter. Here it's constant. But in the case of the diagonal beam, it's not constant. This point here, that's 1 kilonewton over meter. And then this point here, that's 2 kilonewtons over meter. As you can see, here the force distribution varies. I will now find the resultant forces and their equivalent locations for each section separately. Now, I could use integration to get my resultant forces. However, it's not necessary. You simply calculate the areas under the distributions. For the diagonal beam, you essentially have to get the area of a trapezoid, which in fact consists of a rectangle and a right triangle. So let it be FRD, which stands for FR diagonal, it equals the area of the rectangle, which you have here, plus the area of the right triangle, which you have here. And in this context, these areas will be forces, so they will be newtons. And so you will have 1 kilonewton over meter, which is this one here, times 1.8 meters, so it's this one here. With that, you get the area of the rectangle, and then to that, you add 2 minus 1 kilonewton over meter, so you have 2 here, then here you have 1 kilonewton over meter, and so 2 minus 1 equals 1 kilonewton over meter. Then times 1.8 meters, so it's this length here. But right now, you also get the rectangle. In order to get the right triangle, you have to divide it by 2. And then you get the right triangle. And then all that equals 2.7 kilonewtons. That's the entire area of this trapezoid. You can see why you end up with kilonewtons. Your meters get cancelled out here and also here, so you are simply left with kilonewtons. Then FRH, the resultant force for the horizontal beam, well, that's easy. 1 kilonewton over meter times 1.2 meters. The meters are cancelled, and you have 1.2 kilonewtons. You already know that in the case of the horizontal beam, FRH will act in the middle of this force distribution. So if the length of the beam is 1.2 meters, then you will have here 0.6 meters and 0.6 meters. However, to find the equivalent location for FRD, you can now use integration. Let's find it from point A. So our distribution function per unit length is the following. Here you have 2 kilonewtons over meter, just like here. Then here you have 1 kilonewton over meter. Here the length is 1.8 meters. Here it's 0. And so essentially this location here, that's your point A. That's this one. We already have the resultant force due to this distribution. And now I will calculate the moment about point A due to it as well. And I will do that by integrating this function from L equals 0 till L equals 1.8 meters. Here I have the differential element. Its width is dl. If I multiply dl by its height, then I will get the differential force, which is the area of this differential element. And then from point A, I have the length to this differential force element, so it will be my moment arm for this particular differential force element. Of course, as I integrate from 0 to 1.8, I will keep having new and new differential force elements, and also the moment arm constantly changes. And so the moment about point A equals the integral that you evaluate from 0 till 1.8 meters, and then you have the distribution function times L, which is this one here, times dl. Now the thing is that we don't know this distribution function mathematically, but it's quite easy to get. Essentially this function is like a times x plus b, so it's a straight line function. Now you know that this b, it's 2 kilonewtons over meter, because this is where this line crosses this vertical axis. And you also know that your A is negative because it's your slope. It's the slope of this line, but your line is going down, so the slope has to be negative. And to get the slope, you take this piece here, that's your delta WD, then this section here, that's your delta L, so your A will be delta WD over delta L, which is minus 1 over 1.8. So that's your slope. And then this x here, that's actually your L. And then this y, that's your WD. And so that means that the function of this line is WD equals 2 minus 1 over 1.8 times L. And now we go back to this function. Remember that this expression here, it was simply L times dfd. It's this one times this one, and that gave you the differential moment. And then as you integrate from 0 to 1.8, you will add up all the infinitesimal moments, and you will get the resultant moment about point A. And so now that you know this WD function, you will write the integral from 0 till 1.8. This is instead of WD times L times dl. You can also open the parentheses and then rewrite the integral like this. Then this is the first term, then this is the second term, and then in the end you will have this result, which will give you 2.16 kilonewton meters. That's the moment about point A due to this trapezoidal force distribution. And now you have FRD times L bar from point A, and that's your MRA. Then L bar A equals MRA over FRD, and that will give you 0.8 meters. And there you go. This FRD, which is 2.7 kilonewtons, it acts 0.8 meters from point A. Then since the total length of this beam is 1.8 meters, it means that the other part here is 1 meter. And there you go. This force system here is equivalent to this force system here. Just like this force system here is equivalent to this force system here. And as you can see, if you place your resultant forces in the right places, you don't need to add couple moments to these diagrams. But remember, this diagonal beam, it's at 60 degrees from the horizontal line. Then of course, both forces are perpendicular to their respective beams, and because of that, we can say that here you have 30 degrees. Then you already know that this section is 0.8 meters, this section is 1 meter, this section is 0.6 meters, and also this section is 0.6 meters. And then we can also define this length here to be delta x and this length here delta y. Essentially, I have a right triangle here. Then as you can see from this image, the hypotenuse is 1 meter, and since I have 60 degrees here, that's the angle between this diagonal beam and the horizontal line, then my delta x is also a horizontal line. So that means that I have 60 degrees here. Thus, I can say that delta x equals 1 times cosine 60 degrees, and delta y equals 1 times sine 60 degrees. Then I can also take this FRD vector and I can decompose it into its x and y components. So FRD vector equals 2.7 times cosine 30 degrees times I minus 2.7 times sine 30 degrees and then j. You can see that according to our convention here, it has a positive x component and a negative y component. So let me just say that this is FRDX and this is FRDY. Also remember that FRH vector equals 0i minus 1.2j. And of course, both forces are in kilonewtons. And now we are in a position to calculate the total moment about point B due to these forces. So let it be MRB. You have FRDX, which is this component here. So we can draw it here as well. That's your FRDX. And you multiply that by delta Y, by this one, because that's your moment arm between FRDX and point B. And it will give you a counterclockwise moment. Then to that you add FRDY, which is this component here. We can also draw it here. And now we multiply that by its moment arm till point B, which is delta x plus 1.2 meters. So it will be this one here, right? The horizontal beam is 1.2 meters, but you also have to add delta x to it. And then of course, in this case as well, the moment that you have is counterclockwise. And then finally, you take FRH and you multiply it by 0.6 meters. So it's this force and this is your moment arm. And again, it's counterclockwise. So let's put some numbers in now. This is your FRDX times sine 60 degrees, which is your delta y. Then this is your FRDY times all this. Remember, your delta x is cosine 60 degrees. We can simply omit the ones here. And then you have 1.2 times 0.6. That's your 1.2 and that's your 0.6. They are all positive because they are all counterclockwise moments. And so in the end you will have 5.04 kilonewton meters counterclockwise. As you can see, even though some of your force components are negative, like this FRDY or FRH, they all produce a counterclockwise moment about point B. That's why they are all positive, and the final result is also positive. And then you have to calculate the total resultant force. So FR equals FRD plus FRH. I only have one I component here. That's my FRDX. And then I have a J component for my FRDY and FRH. So this is my FRDY, this is my FRH, and in the end, this is my final resultant force. I can also calculate its magnitude, so I will have the square root of, and then all this, where I square both terms and then I add them together. It will give me this result, or approximately, it's 3.46 kilonewtons. And now I will again draw this beam with two sections. I'm gonna place my FR at point B like this, and I more or less know that this vector points in this direction because I know that it has a positive I component and a negative J component. So it's somewhere in the fourth quadrant. And then to that, I will add my counterclockwise moment, which is 5.04 kilonewton meters counterclockwise, and there you go. You can replace this entire force distribution system that you have here, as complex as it seems. You can very simply replace it with this one here, and they are equivalent to each other, just like they are equivalent to this one here. Thank you very much. Welcome back. I have a wall here. It consists of two plates and wet concrete in between. That's the gray color. This wet concrete exerts pressure distribution along the wall as shown in the image. Here you are seeing it from the side in 2D. In 3D it looks something like this. Note that we assume that the positive Z direction is down. Also, the wall is 4 meters tall and 5 meters wide. As you can see, the pressure distribution is constant along the width of the wall. Let this point here be A and this point here B. Now this entire force distribution can be replaced with a resultant force that will act through a special location, making these two representations equivalent. That means that the moment that this distribution of force causes about point A is equal to the moment Fr times Z bar. It will be in kilonewton meters and counterclockwise. And it makes sense because the force distribution and Fr at Z bar are absolutely the same for rigid bodies. And so this moment can cause this wall to tip over. To counter that, a bracing strut is placed, this orange one, such that one of its sides would go through the line of Fr in order to neutralize this moment. So this height here, this H, that's your Z bar. If you place this strut too high or too low, you will have a distance here, let's call it L1, and distance here, L2, and so it will still create some moments that can be a problem. For example, you could have M1 equals Fr times L1, that would be a clockwise moment, or M2 equals Fr times L2, That's a counterclockwise moment. And so your job is to find the correct H so that one of the sides of this strut would touch the wall at the location where you have the line of action of this FR force. So good luck, give it a shot, and the solution is in the next video. Thank you very much. Welcome back. So let's now figure out how high we need to place this bracing strut to completely neutralize the moment due to this pressure distribution. In our case, positive Z went down. However, for my convenience, I will represent the positive Z in this direction. My vertical axis will be the force distribution per unit length, so in kilonewtons over meter. And then I draw this distribution. Since the height of the wall was 4 meters, my final Z is also 4 meters. So this point here, this is your A, and then this origin, that's your B. Note that this pressure distribution function here was given to you in kilopascals. In other words, in kilonewtons over meter squared. To represent this distribution in kilonewtons over meter, you have to multiply your initial pressure function by the width of the wall, which is 5 meters. You can do that because the pressure does not change as you go along the width of the wall. So that means that W equals pressure times 5 meters. This is the pressure distribution in kilonewtons over meter squared times 5 meters. And so you're left with W equals 20 times Z to the power of 1/2, and that's in kilonewtons over meter. So the total resultant force due to this distribution is the integral from 0 till 4 W times dz. That will give you this integral, so you will have 20 over 1.5 times Z to the power of 1.5, and you evaluate it from 0 to 4. So you will have this result, or approximately 107 kilonewtons. Then the total moment about point B due to this distribution is MRB equals, again you have your integral from 0 to 4, you have W times Z times dz, so that's your integral. You can also write it like this. And so if you evaluate it, then you will have this result, which is 256 kilonewton meters. And so the distance of FR from point B can be calculated like this. FR times Z bar sub B, so we are measuring it from point B, from above, it equals MRB, and so Z bar sub B, it equals the moment over the force, so 256 over, and then this is the exact value for my resultant force, and I will get 2.4 meters. That means that this force, FR, it's 2.4 meters away from point B. That means that your Z bar, or in other words your H, which is this one here, it's the remaining length. It's the one that you measure from point A. Since the total height of the wall is 4 meters, you will have 4 minus 2.4, which is 1.6 meters. And there you go. The height of the bracing strut from the ground should be 1.6 meters. That's your answer. And now, if you look at this 3D wall, then since the pressure distribution was constant along the width of the wall, and the width of the wall was 5 meters, then because of that, this FR vector would act 1.6 meters from the ground, that's your H, and horizontally it would be in the middle. So you would have 2.5 meters from one side and from another side. And this point that FR is applied to, it's called the center of pressure, or simply CP. So this point here, that's your CP. Every time you find a point through which a resultant force of some kind of distribution acts, you are actually finding the center of pressure of that distribution. So in this case, this point here, that's the center of pressure of this pressure distribution. Thank you very much. Welcome back. I have a general load case here where this orange plate is subjected to the following load. P equals, and then this is the function, and it's in kilopascals. As you can see, it's a multivariable function, so your pressure depends both on x and y. These two axes here are x in meters and y in meters, and then the vertical axis is the pressure, not z, but pressure in kilopascals. And you can see the necessary dimensions of the plate here. The task is very simple. Find the total resultant force due to this load distribution and its center of pressure on this plate. You have to find it in terms of x and y coordinates. So try it out by yourself first and then see the solutions in the next video. Thank you very much. Welcome back. Let's now find the total force due to this load distribution and its center of pressure. You have this pressure distribution function here, and what I'm gonna do, I'm gonna open up these brackets and these parentheses. If I do that, then I will have pressure as a function of x and y equals this result, or even better, this result, in kilopascals. To get the total load due to this pressure, you have to integrate that function over the entire area of the plate. So you have a small differential area here, which is your dA. Then this is your differential force that acts on this differential area. It equals pressure at this particular point. So pressure at x asterisk and y asterisk times dA. However, this differential area, dA, it consists of dx and dy, which means that dA equals dx times dy. Therefore, this differential force equals the pressure at the location where your dA is, and instead of dA, I will have dx times dy. So the total force equals the integral of df, where I will sum up all the infinitesimal differential forces as I sweep through this area, or I can write the integral of pressure times dA, or I can have double integral. The outer integral goes from x equals 0 meters till x equals 3 meters, from here till here, and the inner integral, it goes from y equals 0 meters till y equals 4 meters. And now my pressure function is this one here, and now I'm going to put here dy and dx. It has to be dy and then dx because this is my inner integral. I will evaluate this one first, and then I will evaluate the outer integral. If I want to write dx times dy, then my outer integral needs to have y's here and the inner integral the x's. And then I will still have my pressure function here. And so let's first evaluate the inner integral. Let it be 1. So this is how it looks like. Note that since I'm only dealing with the y dimension right now, I treat x's as constants, and so I can take them out of the integral. So if I evaluate this integral, then I will have this result, which will be this one or this one, and this here is my final result for this inner integral. And now I take the outer integral, and now inside this outer integral I'm gonna put this result here that I got from my inner integral. So it's 16 over 3 times x, and now I have dx. And now since I have dx here, my x is not a constant anymore. Now it's a variable. If I evaluate it, then I will have this result, or simply 24 kilonewtons. And that's my total force due to this entire pressure distribution. Once we have our total force, we have to calculate the total moment due to this distribution about the x-axis and the y-axis. So let's do that. So again, on this plate you have your differential area, dA. It experiences a differential force element, and that's why you get the total force when you integrate across the area. You sum up all the dFs. If you now want to get the total moment about the x-axis, you have to multiply this dF by this distance y that separates you from this x-axis. And so you do it here, you do it here, then you also do it here, so you do it everywhere. You go through the entire area of the plate. You sum them all up with an integral, and then you will get the total moment about the x-axis. You can see that according to the right-hand rule, it will be a negative moment, because your right-hand thumb will point in the negative x direction. That's because all forces point down, and in this configuration, where all your y values are positive, the tendency of rotation about the x-axis is as I have drawn here, in the negative x direction. And then you do the same thing in order to get the total moment due to this pressure distribution about the y-axis. For each differential area, you will have x times dF, so the perpendicular distance between the line of action of dF and the y-axis, and you sum them all up with an integral. And then, according to the right-hand rule, you will get a positive moment about the y-axis. And so, let's do that. The moment about the x-axis will be y times dF, and then you integrate that, or you can write y times the pressure function times dA, and so it equals this double integral. Let's evaluate the inner integral first. So this is your inner integral. You can rewrite it like this, and so this is what you will get. This is a more compact form, and this is the final result of the inner integral, 64 over 9 times x. And that means that mx equals, this is your outer integral, this thing here, that's the result from your inner integral. If you evaluate it from x equals 0 till x equals 3 meters, you will get this result. You can cancel out the 9s, and you will be left with 32 kilonewtons times meter. So that's your total moment about your x-axis, and it's in the negative x direction. And now, the moment about the y-axis, that's the integral of x times df, or x times p times dA, or as a double integral, it looks like this. So again, we evaluate our inner integral, let it be 1. This is how it looks like. We can rewrite it like this. This is what you will get when you evaluate that. You can cancel out the 2's here, and in the end you will get 16 over 3 times x squared. So that's your inner integral. And then the total moment about the y-axis, you get that when you integrate the result of the inner integral. So this is what you will get. You can cancel out these 3's here and the power of 3 here. It will just be 1. And so in the end, you will have 48 kilonewtons times meter. That's the total moment about the y-axis due to this pressure distribution, and according to the right-hand rule, it will be in the positive y direction. So this one is your my. And now, to find the center of pressure, you first have your total force, which is 24 kilonewtons. Then this is your center of pressure in the y direction. That gave you the moment about the x dimension. And so you can calculate your y bar Cp like this. You have 32 over 24. You cancel out the kilonewtons, and you will have 4 over 3 meters. And then you write the same force times x bar Cp, your center of pressure in the x dimension, and that gave you the moment about the y direction. So your x bar Cp equals my over f, 48 over 24, that's 2 meters. And there you go. This is your y bar Cp, this is your x bar Cp. They cross here, so your resultant force acts through this point, because this point here, that's the center of pressure of this load distribution. For as long as we have our rigid body assumption, this one and this one, they are equivalent to each other. Thank you very much.